Good morning, guys. So we are starting with the portion from where we left off. Right, we talked about potential energy, which is U, and we talked about what potential, which is V. Potential energy is the work done to bring a mass from infinity to a point in the field of a source mass. Hence, we found the potential energies equation as minus Gmm by R, where m is the source mass into whose field you are trying to bring a small mass m from infinity, right? And when you bring the point or mass from infinity to this point, let's say P, then this point and this mass location, the distance between them is r. Then u is equal to minus Gmm by r. Similarly, we dealt with the term potential, that is work done to bring a unit mass from infinity to a point, right? So the expression of v also we found like this. So you can see easily that there is some relationship which we can build with respect to u and v. That is, if I write u by m, I can write it as v. So u by m, that is potential energy per unit mass, is also called what? Potential, right? So there is an expression you can deal with the, you can find from the above two equations, very easy, right? Now continuing on, now the section which I am going to take is only NEET oriented or entrance oriented, not the in your textbook, right? That is the relationship between E, that is our field, or you can sometimes it is also called a field intensity, right? Relationship between field intensity, or you can just say gravitational field energy or gravitational field and potential, relationship between E and V. It is experimentally, it is actually, it has been derived in a lengthier process. You need not go for the details. Just know that E is equal to minus dV by dr. Gravitational field is equal to minus dV by dr. There is an expression. Continuing with the topic itself, that is gravitational. Okay, I could have written just V now. Gravitational potential due to solid sphere, then we'll go with spherical shell. So no need to go over details, very easy. We are going to consider if the point, or you want to bring a mass from infinity to a point here, which is at a distance r, right? So you want to bring a mass m, let's say from this point to this. Let's say this is the source mass, which is capital M. So you are having a situation where r is greater than capital R. Capital R is the radius of this mass, right? So in this situation, it is V out, right? That is a potential at the outside point is equal to minus Gm by R. That is the distance between these two masses. Now, right, I have brought small m from this point to this point. So, minus Gm by R. Now, B, if I am going to bring the mass from infinity to the surface, that is, I am going to bring and keep that mass over here, then R is equal to capital R. That is, we are having to find the potential at the surface is equal to minus Gm by capital R. Right. Now see what happens if I am bringing the mass from infinity to inside the solid sphere. Right. So that this is the distance now, which is R. Now you just have to write the relationship, right? Most of the time it is directly asked, the question is directly asked. So V in, that is the potential inside, will be minus Gm by 2r cube into 3r squared minus small r squared. Just mark up the equation, right? Similarly, there is an extra point, that is D, that is V at center, that is exact center here, right? V at center is actually found to be 3 by 2 times V surface. right? Experimentally as well as calculation wise, both has been proved. So you just have to by heart the equation on the basis of your our NEET or any entrance section. You need not go for the derivation part. Right, now just like the previous case, we are going to depict the graphical relationship between V and R. Just like this, we draw a relationship between E and R, right? Just like that, we're going to draw for potential. Right, so we have two negative values itself, right? So obviously I will write it in the negative section. This is minus gm by r, and there is another one which is greater than, that is minus 3 by 2 gm by r. What is minus 3 by 2 gm by r? This is at the center. So maximum then goes on reducing at r, at surface, right? You're having minus gm by r. So here, then it goes on reducing. Right, so this is the graphical representation. So when r increases, right, potential decrease, because in the denominator section, r if it increases, when denominator increases, the factor decreases. Right, now we'll talk about our same potential, but regarding what? Spherical shell. Shell means it doesn't have anything inside, right? So just like the previous cases, for cases r greater than capital R and r equal to r, that is in the case of V out and V surface. V out is just like the previous case, minus gm by r. V surface is minus gm by capital R. Just like the previous case, only changes were when r is taken very less than, when not very less than, very less than, just you are going to consider the point is inside the hollow sphere. So V in is equal to also is minus gm by capital R. That is, this is very important. In the case of spherical shell, if the potential here is something, suppose it is 20, right, then the inside part also has the same potential. Once the potential is distributed on the surface, the same work is to be done if you are trying to bring it inside, right? Clear? So it is not like electric field. Electric field in the case of hollow shell, inside it is 0. No, that is not similar here. Here the potential inside as well as surface is having same magnitude. Hence when you plot a graph between V and R, it will look like this. And this is a maximum value R, this is minus gm by R. Clear? This is 0. Clear? Now we'll move on with our I believe we can move on to the syllabus portions, right? Clear? So this is actually syllabus portion itself, but I am taking it in topic wise, so that it is very easy to write notes based on it. That is gravitational potential energy of a system of two particles. That is, if there are two particles like this, let's say this is m1 and this is m2, and let's say their distance is r, so you will write u is equal to what? Minus g m1 m2 by r. Sorry, why did I write r2? This r, right? So potential energy of a system of two particles. Easy, right? Now B, gravitation potential energy for three particle system. That is, here it is m2, this is m1, and this is m3, right? They are kept at the three corners of a triangle. Let's say this one is r13, this is r12, this is r23, right? So u is equal to, between these two guys, is minus gm1 m2 divided by r12 plus, right, then comes minus gm1, right? So I can remove my plus here, minus g m2 m3 divided by r23, right? Then minus g m1 m3, right? Or I can write m3 m1 divided by r13, or I can write r3 once, okay, right? So you go on adding if this is 3 particle system like this, if you are having n particles, you can write for that also, very easy, right? So this is how you write for gravitational potential for 3 particle system, right? So total gravitational potential energy of the system is the sum of the gravitational potential energy of all pairs. Clear? Easy. Now someone asks you change in potential energy or work done to raise a body, say of mass m, to a height h above the surface of earth. So this is our earth. Let's say the earth is having mass m and its radius is capital R, right? Suppose this is a mass small m. I want to raise the small m from this position to this position so that this height is h. Alright, so now this position of m will change to here, right? So initially here position will be having a potential energy ui is equal to minus gmm by 1. From center of earth I am measuring, it is r. Whereas here final potential energy will be minus gmm by r plus h, that is the height, right? We are measuring from the center of earth, so it will be r plus h. Easy? Yes. Clear? So someone is asking you change in potential energy, that is work, right? So that is change in potential energy, right? So it is, what is potential energy? Final change in potential energy is final potential energy minus initial potential energy, that is equal to minus gmm by r plus h. Minus of minus becomes plus gmm by r, right? I can bring gmm as common outside, so it becomes gmm, right? In the bracket I can write 1 by r as positive, so 1 by r minus 1 by r plus h, right? Clear? So that is equal to gmm, right? Bring this guy r plus h minus r divided by r into r plus h. Then r cancels, so there is only numerator h, right? So I'm rubbing it off. So h divided by r plus h, right? That is equal to gmm h divided by r squared plus rh, right? Let me bring r squared common from outside, gmm, right? h divided by r squared, then it will be 1. And there is, if I want r squared here, that means I have to multiply numerator r and then denominator r. So when bring r squared outside, there will be h by r, right? Clear? Right? So now you have gmm h by r squared, right? gmm h by r squared into 1 by h by r, right? Now gmm by r squared, right? Or I can just say gm by r squared is our g, that is acceleration due to gravity, and there is m and there is h, right? Now I'm going to just rearrange it and I'm writing it as mgh. This mgh into 1 divided by h by r, right? Right? I'm bringing r in the numerator section, so it becomes mgh into r divided by r plus h. Right? This is the work done or change in potential energy to bring a mass from the surface of earth to a height h. Right? It's something which you can derive without my help, but it is better if you have a small equation to help you out. Right? That is, if you are rising, suppose the object from the earth's surface to a height such that height is very less than when compared to the radius of earth, then I can say this most part will be very much neglected. This h is very small, so r and r can cancel and you will get the work done is mgh. This is the equation which you usually use, right? Work done to bring a mass from this point to this point. So you write work done is equal to mgh. Now what happens if the height to which the object has been raised is equal to the radius of earth? Then work done will become equal to mgh into r plus r, that is r plus 2r. So r cancel, I can write mg, right, r by 2. Let me check. Why did I make a mistake? H and R are equal, so mgh r divided by 2r, no? So mgh by 2, right? Now if h is equal to nr, to some height which is very greater than radius of earth, so it becomes mgh r divided by r plus nr. So r cancel, so I can write mgh into 1 plus n, right? Clear? Or h is equal to nr, no? So here also I can change mgh, it is equal to r, so I can write mgr by 2. Or here also I can write mg, in place of h I will write it as nr, right, into 1 plus n. Why I write it as n, right? So I can write mgr n divided by 1 plus n, right? So you got the expressions. So I hope you can write it in your book, right? Now the equation which I am going to write is strictly meat based. It is someone is asking you velocity with which a body will hit the ground when it is brought from a height edge. The same case of earth itself. This is earth, right? So initially, suppose for this I'm going to consider that initially I'm throwing a ball v in. At maximum height the velocity becomes 0, right? Let's say the height achieved is h. So I have thrown the ball which is of mass m, and m is capital M and radius of earth is r, right? So the expression you are going to find is actually velocity which is required to project a body to reach a height, right? This is not escape velocity, guys. Escape velocity is something which I will take later on. You are asked what will be the velocity required to project a body from the surface of earth to height h above it. Height is something is given, then you can write, right? So keep this in mind. This is not the velocity which is required to move the object above as a condition that it will be outside our gravitational field. No, it is said that how much velocity is required to bring the object from the surface to the maximum point of height. That's it, right? So here you are using the conservation of mechanical energy, right? So at the surface you will be having kinetic energy as well as potential energy of surface, right? That should be equal to total energy in the case of final situation, that is kinetic energy with potential energy at final stage, that is a conservation of mechanical energy. Now here at the surface I can write kinetic energy has half m v squared and potential energy is minus gmm by r, that is at the surface. Maximum situation there is velocity is 0, so I can write kinetic energy as 0, right? And at the final situation the potential energy is minus, no, sorry, so it is minus gmm by r plus h, right? Clear? So here I am going to bring this guy over this side, right? So that means half mv squared is equal to gmm by r minus gmm by r plus h, right? So I bring gmm outside, 1 by r minus 1 by r plus h, right? And this half mv squared is this factor, right? Earlier we have done this section, I hope you remember. So you will get mgh divided by 1 plus h by r. Go through the earlier derivation, we have done it. Half mv squared, right? So I can cancel mm here. You will get v squared is equal to 2gh divided by 1 plus h by r. right? Or I can write v is equal to root of 2gh divided by 1 plus h by r. That is, this is the velocity by which you have to throw an object from the surface of earth so that it achieves the height h, right? And this is also the velocity with which a body will hit the ground when it is dropped from height h. Velocity to reach height h, velocity by which it reaches down. That is, v is equal to root 2gh by 1 plus h by r. Right? Clear? Now this and all are NEET oriented topics, guys. It's okay, right? So this is not there in your extra or your exactly, I would say, in your textbook based section. So now maximum, next section is maximum height which is attained when it is projected with a velocity say v from the surface of earth. So that is, if you throw an object from the surface of earth with velocity v, how much height it can achieve. So we are going to find the expression for it, right? So same diagram actually, right? The earth is here, it is having mass m and its radius is r, and this is its initial position. You are having a final position where the final velocity becomes 0, and you are throwing with the velocity v and a height is achieved h. You are going to find the expression for this one. So we already found the velocity by which it can be thrown so that it reaches the maximum height is 2gh divided by 1 plus h by r, right? Now here I am going to bring this guy over this side, becomes v squared plus v squared into h by r is equal to 2gh, right? So v squared is equal to 2gh minus v squared h by r, right? Now from these two guys I am going to take h common, so it becomes 2g minus v squared by r, right? So from here I can get the expression of h as v squared divided by 2g minus v squared by r, right? Or I can write v squared by 2gr minus v squared by did r can go up, so that now the expression becomes v squared capital R divided by 2gr minus v squared. Now this is the expression you can go for the maximum height which is achieved by an object which is thrown from the surface of earth with the velocity v divided by v squared. Again I am repeating, this is a NEET question, guys, not there in your textbook. Clear? Right. Now again there is a topic which you have to know, again is NEET oriented. This is self energy, not there in your textbook. Self energy of bodies. That is the energy which is possessed by a body due to the interaction of the particle inside the body. That is, we consider a body as a system of particles, right? So this system of particles, each particle will be interacting with each other, so they will be possessing an energy by themselves that is known as self energy of that body, right? Single particle doesn't have self energy, right? That is, for the other body, self energy of the body is a negative work done by the gravitational force, right? See, suppose each particle I am considering as an individual body, so I have to do some work extra to bring them, right, and to keep them collected against the gravitational field, because gravitational force will be trying to pull them out, right? So if they have to keep themselves into an entity itself, so they are doing a work, right? Each particle will be doing an attractive work between each other, right, against the gravitational force which is trying to bring them apart, right? Clear? So that is actually their self energy. So self energy is always an interactive energy. So it's the same two equations you just have to know, that is self energy in the case of hollow sphere and solid sphere. So self energy is, okay, I will write it as energy itself, energy of a hollow sphere, that is equal to minus gm squared by 2r, right? And self energy of a solid sphere is equal to minus 3 by 5 gm squared by r. Right, these two expressions, please by hearted. Clear? Right, the next topic which I have to move on, which is there in your textbook and very important, is escape velocity. Its derivation is repeatedly asked in most of the examination. What is escape velocity also is asked as a 1 mark question. So someone asks you the definition of escape velocity. Escape velocity is the minimum velocity which is required to escape from the gravitational field of a body, right? And it depends upon the mass of the, suppose it is a planet, so this is Earth or whatsoever planet, so you require a particular velocity by which you can throw the object so that this object escapes the gravitational field of this mass or this planet. That is known as escape velocity. Clear? Right. This escape velocity only depends upon this mass of the planet and the distance to which it has to be thrown. Right? Clear? Now that for that we are going to do a derivation part, guys. Clear? Right, after this we to try by this video I will finish off the theory section. I hope we can finish off the theory section and we will go for the numerical section if possible. So we are going to derive the expression for escape velocity, right? That is, suppose you are having a ball in your hand, right? So this is earth and this is you standing, right? And you are having ball in your hand, means let's say that ball is at a height h from the earth surface, right? And let's say this is center of earth, so r is the radius of earth, and you want to throw the ball so that it escapes the influence of gravitational field, means you want to throw the ball to infinity, right? So initial position is this one, final position is this one, right? So at final position also you can say that the total energy should be some equation. Similarly, initial position also will be having total energy. So I can say conservation of energy, total energy at the initial point should be equal to total energy at the final point. Yes. So we are going to derive the same type of equation we have just derived, but this one is explicitly your school based. Okay, so total energy at infinity should be equal to total energy at initial, right? Okay, so first let us talk about total energy at infinity, right? So total energy at infinity will be equal to kinetic energy at infinity plus potential energy at infinity, right? So kinetic energy at infinity, I can write it as half m Vf square, where Vf is the final velocity achieved, and potential energy at infinity will be minus gmm by r. Let's say the ball has reaching a maximum height here, which is at a distance small r from the center of earth, like this. Clear? Very easy. Now when r is infinity, right, this term goes off because 1 by infinity is 0, right? So I can just write total energy is equal to half m Vf square, right? This becomes the first equation. Clear? About the initial position, right? We'll derive the total energy in the initial position. So at initial position, right, so kinetic energy will be what? Half mv square, or let's say vi square, that is initial velocity, and potential energy, let's say it is what? Minus gmm by r plus h. Why r plus h? See, the ball is at a height h plus r from the center of earth. We are taking the measurement from the center of earth, so this is the potential energy. So total energy will be sum of these two, guys. Total energy will be half m vi squared plus, right, so in place of plus it will be minus, right, because this minus comes up, minus gmm by r plus h, right? So you got the second equation, and you got a first equation and you are getting second equation. And you know conservation of energy, first equation should be equal to second equation because total energy initial should be equal to total energy final, right? So I can write half m Vf squared, which is the total energy at the final stage or at infinity, is equal to half m Vi squared minus gmm by r plus h, right? Now see this guy, right, this value will be always positive, right? Because final section, if you take this entire term, you never see what it is a square component, guys. Mass is never negative and half is a constant value and Vf squared. So this term always will be positive. So I can say if this is positive means half mvf squared is greater than 0 or greater than or equal to 0. That means if this is greater than or equal to 0, then this term is also greater than or equal to 0. That is half mvi squared minus gmm by r plus h is greater than or equal to 0. That means it is positive. Clear? Let us bring this guy to here. In place of greater, I am going to equate it as equal. That is half mvi squared is equal to gmm by r plus h. What is a better way of solving the problem? Right. So we can cancel this m and this m. Right. So I can write vi squared is equal to 2gm gm divided by r plus h. Right. And we are going to assume that we are going to throw that ball, or we are handling, we are very small when compared to earth, right? So if you hold the ball in your hand, when compared to the radius of earth, this height is very small, right? So I can neglect this h, right? So that, see, h is very small when compared to the radius of earth. So I can neglect h part, means this part goes off. Right, so vi squared is equal to 2gm by r. I can write vi is equal to root 2 gm by r. This is the expression for escape velocity. Now in place of vm, I am going to replace it with e to suffix that this is escape velocity. Velocity by which an object has to be thrown so that it escapes the gravitational field of Earth or any planet. R is the radius of that planet or Earth. M is the mass of the planet or Earth. So as you can see, the escape velocity depends upon only M and R, and of course G is a gravitational constant. Right. Now someone asks you to write this entire expression in terms of acceleration due to gravity, that is writing the escape velocity in terms of acceleration due to gravity. How would you write? See, you know g is equal to gm by r square, right? Let us bring one r over this side, so it becomes gr is equal to gm by r, right? So when I multiply 2 in this side, this would be also 2, right? So 2gr is equal to 2gm by r. So I can write here escape velocity is equal to root 2gr. So this is another expression for escape velocity. Clear? Right. Now very easy to derive this equation, and I am repeatedly telling you guys, this question or this derivation is always asked, right? Yeah. Now going on, the escape velocity, this is something which I am going to talk from my side, right? So you can put this value g into is equal to 9.8, and you can put r's value as what, 6.4 into 10 to the power 6 meter, or this 6,400 kilometer. So standard escape velocity of earth is 11.2 into 10 to the power 3 meter per second. This is the escape velocity which is required to, if you want to throw an object from so that it escapes from the gravitational field of earth. Alright, that we can see that escape velocity does not depend upon the mass of the body, right? That is, what you are going to throw is irrelevant, right? It only depends upon mass of the planet and radius of the planet from where you are wishing to throw that object outside, and it doesn't even depend upon in which angle you are projecting, right? Clear? Right. Now escape velocity of a body from a location, suppose, which is at a height h above the surface of the planet, right? Suppose this is something which I am telling from my side, guys. This is earth. Suppose the height is very large, right? It is not that small when compared to the not small when compared to the radius of earth, right? H is quite little bit large. Then the expression has to be changed for escape velocity. You will write it as escape velocity is equal to root 2 gm by r plus h, right? Clear? right? Right now, whereas suppose so we want a body, right, it is having a mass. Let's say that body is having a mass or m. If it has to become a black hole, then its radius should be decreased in such a way that the escape velocity of a black hole, if you are supposed that you want to make an object into a black hole, then that black hole section should be having, or that body should be moving with a velocity of 3 into 10 to the power 8 meter per second, which is very difficult, right? That is why you say that it is very difficult to generate a black body from artificial process, right? So this much clear. That's why not like even light doesn't escape from an object which is black body, right? Clear. Now this is a derivation section which we are talking only based on need section, right? Read the heading like this itself: expression for height attained by a body in terms of radius of earth or any planet when projected from the surface with the speed of ve by n. That is, if this is any planet, or if you are taking about earth, if you want to project, or when object is projected with a speed of ve by n, how much height it would have attained? That is the question. Clear? So expression for the height attained by a body in terms of r, any of which is the radius of that planet when projected from the surface with a velocity of ve by n, right? Need not go for the derivation part, guys. The height achieved can be written as r divided by n squared minus 1. That is, if an object is thrown up by velocity ve by n, that ve is escape velocity by n, then the height achieved can be written as h is equal to r divided by n squared minus 1. Clear? Similarly, another expression, very important, guys. Right, velocity of a body at infinity when it is projected with a velocity nve from the surface of earth or any planet. That is, if you are projecting an object with the velocity nve, what will be the velocity at infinity, right? Clear? So write the equation: velocity at infinity when an object is thrown from the surface of earth or any planet which is having radius r on mass m, and the velocity at infinity will be v is equal to root of n squared minus 1 into escape velocity. V is equal to root of n squared minus 1 into ve. Where again I am rewriting, guys. This is not there in your syllabus, or I can say in your textbook point of view. Clear? Right. Now the next section which we are going to talk about is Earth satellite. Right. So I know you would have learned a little bit about satellite. There are two types of satellites: natural satellites and artificial satellites. So natural satellites is natural. In Earth it is moon, right? So they are extraterrestrial objects which are revolving around planet or any other extraterrestrial objects itself. This Earth is an extraterrestrial? No, you call an object extraterrestrial with respect to planet, right? Similarly, every other planet also have their own satellites, right? So Earth satellite, natural satellite, is moon because it is continuously revolving around us. Now there is an artificial satellite which is man-made, right? Artificial satellite which is used for communication, for weather forecast, military purposes, spy purposes, right? So this every year, every government of almost all the countries launch their own satellites for different purposes, even for spy section, right? Right. So let us derive the time period of satellite, right? Clear? We are going to derive the time period of a satellite. Now you can suffix as t itself. Now suppose there is a satellite revolving around the earth with, say, it is orbital velocity. VO is the orbital velocity, that is the velocity by which a satellite will be orbiting around earth, that is known as orbital velocity, whose expression also we will derive, don't worry. So first let's say an satellite is revolving around Earth with an orbital velocity of VO. Right, so this planet or this satellite which is revolving around Earth will be experiencing a centripetal force towards the center. Let's say that centripetal force is Fc will be mv squared by r plus h. Why did I take r plus h? Let's say I'm drawing it a little bit larger. This is our Earth and the satellite is here, and this will be r, and this, let's say, is h. So this satellite from Earth's center is r plus h distance. That's why in place of mv squared by r, I wrote it as mv squared by r plus h, where m is the mass of this satellite. Clear? Now gravitational force will be existing between these two guys. Yes. So gravitational force is equal to gm, that is the mass of Earth, into mass of the satellite divided by r plus h whole square. Right. Now for the satellite to remain in its orbit, the centripetal force and the gravitational force should be equal. So I can write Fc is equal to Fg, or mv divided by r plus h is equal to g capital M small m divided by r plus h whole square. Can be cancelled, 1 r plus h is cancelled, so you get this mv is actually orbital velocity, right? So I will write here O, right? VO, right? So VO, I got an expression, VO is equal to root of gm by r plus h, right? This is the expression for orbital velocity of a satellite around a planet which is having radius r and mass r. As you can see, the orbital velocity depends only on the mass of the planet and the distance of the satellite from the planet, right? Now, but the heading was what? We are going to find the time period. So we are moving on to that section itself. Now, while a satellite is revolving around a planet, or we have taken the example of Earth, it will be covering this much circumference. So what is the circumference here? It will be 2 pi into r plus h. That much circumference it is covering, right? And with how much velocity is covering? V0 velocity. So time will be distance by velocity, that is 2 pi into r plus h divided by V0. In place of V0, we are going to substitute this value, so that becomes 2 pi into r plus h divided by root of gm divided by r plus h. Right, that is equal to 2 pi into r plus h, and let us bring this root above, so r plus h divided by root gm. Right, now this is raised to 1 and this is raised to 1 by 2. If you didn't understand, I'm going to rewrite here r plus h raised to 1 by 2. So this is 1 and this is 1 by 2. So you will add, so 1 plus 1 by 2 is 3 by 2. So I can, it is root 2 pi into r plus h raised to 3 by 2 divided by root of g. Right? Easy. Right. Now this is the expression for time period of rotation of a satellite around Earth. This is the actual equation. Special cases now we will discuss. Special cases, right? Special cases, let's say if the distance, this is the planet, and the distance of the planet and the surface of the planet and the satellite, let's say it's h, right? So let's say this h is very small when compared to the radius of Earth. Then r plus h, I can write it as what? R itself. So this term becomes what? This term time is equal to 2 pi, right, root of r cube divided by gm, right? Clear? Right, now we can just split this guy 2 pi r squared into r divided by gm, right? Now what is gm by r squared? It is what? G, acceleration due to gravity. So I can write t is equal to 2 pi into root of r by g. You have seen this equation before. You can relate this equation with our time period of rotation of a pendulum, remember, right? It's quite similar, right? T is equal to 2 pi into root L by G. In place of L, you have just replaced it with R. So this is the condition, or this is the equation which you can see no, when the object or any planet is, not a planet, satellite is revolving around a planet. Time period of rotation. Clear? And the earlier expression, see, you have seen here, T is proportional to R raised to 3 by 2, right? This is something which you have stated as per Kepler's law itself, right? So you can see that Kepler's law is true, right? Clear? Now the next heading or the theory section which you have to know is energy of orbiting satellite. So in case of satellite, we derived the someone asked you derive the escape velocity of the satellite, that also you have derived. Then you derived of what? VO, that is orbital velocity. Then you have found the time period of oscillation or time period of rotation of a satellite around a planet. Now we are going to derive the energy of orbiting satellite. So first let us talk about kinetic energy. You know kinetic energy is half mv squared, right? So when the orbiting satellite is moving, it will be having which velocity? It will be having orbital velocity. So here I am supposed to write as half m VO square. So it becomes half m. In place of VO, I am going to write it as gm by r plus h, right? And the root goes off because of the square section. So half m gmm divided by r plus h, that is kinetic energy, right? Now let us talk about our potential energy. Let's mark this as A. Now let us talk about potential energy, right? Potential energy, what would I write? Right, in place of potential energy, you have already derived the formula as gmm by r plus h. Very easy, right? So someone asks you sum of potential energy and kinetic energy, that is our total energy. Add these two guys, very easy, half minus 1, so it will be minus half gmm by r plus h, right? So you got the expression of kinetic energy, potential energy and total energy. You can see that there is some relationship between these two guys. Now you see potential energies, half is kinetic energy and what? Total energy. So I can say potential energy is equal to double the total energy is equal to minus double the kinetic energy, right? It helps to have this clear, right? Obviously potential energy is negative, right? So that's why you write it as here negative, but total energy and potential energy both are negative, so you can write this expression also. Clear? So if you by heart any one equation, the other guys will come as it is, right? Now some of the theory sections, now by this the derivation part is over, right? Now the sections you have to know is what is a geostationary satellite. Someone asks you, do you know anything about geostationary satellites? And then you have to talk about polar satellites and the weightlessness is in free space. By that the topic, the entire section is completed. Okay. So first someone asks you, what is geostationary satellite? Geostationary satellite, geostationary, okay. Write the heading, geostationary. Right. Geostationary satellites are those which have a time period same as that of Earth, so that their position in the orbit is stationary with respect to Earth. This is like this. Earth is rotating, right? Right. So Earth is rotating by the time period of how much? 24 hours. Now the geostationary satellites also have the time period of 24 hours itself. So if a person who is standing over here sees the geostationary satellite here, So after rotation, this person might be reached here. Then also he will see the geostationary light just above him itself. So the position with respect to Earth, the geostationary satellite's position doesn't change. That's why it is called geostationary satellite. That is with respect to geo, that is Earth, it is stationary, right? That is geostationary satellite. Clear? Right? Now, you do not go for the derivation part, right? So, the radius of a geostationary orbit, right? So this expression again need not no go for the greater derivation parts. It is actually similar as that of the time period which you have derived earlier. So just write down the case of geostationary satellite, radius of a geostationary orbit r, right, is equal to r plus h, right? This is r and this is h, right? So r plus h is equal to g r squared into t by 2 pi squared raised to 1 by 3. Expression only is required, right? And when you substitute this h value, that height by when you substitute g's value, and then you can find the r also, right, in the case of Earth. Then for Earth, the position, right, the position of a geostationary satellite from the center of Earth, which is, let's say, is h, that h is found, or you can say from the surface of Earth, right? The position of geostationary satellite from the surface of Earth, h is equal to 3600 kilometer. This is the position of a geostationary satellite. Easy, right? Now next section is polar satellites. Right, now polar satellites are a little bit different when compared to geostationary satellites. They are of low altitudes. Low altitude means the height by which from the surface of Earth is around 500 to 800 kilometers. Sorry, polar satellites are those which are a low altitude, right? Their height ranges from 500 to 800 kilometers. They go around the poles of the Earth in north-south direction, like this. Suppose this is Earth. Geostationary satellite usually orbits like this, or they can even orbit like this, right? But polar satellites always orbits like this. From north to south poles, it revolves like this, right? So they are polar satellites. The Earth will be rotating around the axis in east to west direction, right? Whereas our polar satellites move from top to south like this, or north south direction, or north pole to south pole, right? And its time period is 100 minutes. Since its time period is 100 minutes, it crosses Earth many times a day. Geostationary satellite rotates very less, right? Whereas our polar satellites will be rotating with a high speed, right? So they cross the Earth in every 100 minutes. Clear? These satellites can view polar and equatorial regions at a closer distance with good resolution. Right? Information gathered from such satellites are useful in remote sensing, for meteorology, for environmental studies. See, actually what they do is, this is not their textbook, I am something giving you from my side. See, polar satellites, they are not actually exclusively meeting the poles. They can even move from here to here, north to south. Then they get a strip information from here, right? Similarly, polar satellite will move from here to here. So they got the strip information from this section. Like that, they will be moving so that the entire Earth's surface will be covered by them in not fractional seconds. Very easily they will cover, right? That is the plus point of polar satellites. Clear? I hope this much is clear. Right. So next topic, this is the last smallest topic, that is weightlessness in space flight. See, a body in a satellite orbiting around Earth experiences an apparent weightlessness. This is because its weight W, right? It is used to provide the required centripetal force for circular motion, right? A body outside, it has to revolve around Earth, right? So the weightlessness means the weight which is used is providing the centripetal force towards the center, towards the Earth, right? It is not that the apparent weight of a freely falling body, right? We know that it is zero, right? Hence, a body in an orbiting satellite is equivalent to a free falling body, right? That is when a body which is revolving, let's say around earth, so this is our earth, right? His entire weight is used for what? For counterparting the gravitational field, right? So everything else is negated here, right? So the end. Okay, let us go on with the numerical section, guys. I'm sorry if you're hearing a disturbance, some work is going on near my home. Okay, so suppose you are having a particle, let's say mass m. It is kept inside a spherical shell which is also having mass m, and say this is the radius r, which is of the spherical shell's radius, right? You are asked what is the gravitational potential at a point p, which is equal to r by 4 from the center. This is center. So you are asked what is the gravitational potential at this point, which is at a distance r by 4 from the center. This is the question. This is the point P. So the point P will be experiencing potential due to this mass as well as this mass, right? That it will be experiencing first, let's say potential at P due to, this is due to the particle, this particle, right? Due to particle, right? Let's say that is Vp, and 2 potential at P, I am writing as V dash P due to the shell, right? So the net potential at P will be potential due to the particle plus potential due to the shell. This much clear? So what will be the potential at P due to the particle? So this point P, let's say this particle is at the center, is at a distance r by 4 from the particle, right? So I can write Vp is equal to minus gm by r, right? So in place of r I will write r by 4, right? So this becomes minus 4 gm by r, minus 4 gm by r. Now what about the shell? This shell, right? So potential at P due to the shell, that also we have found it as when the r is very less than r, capital R, that is the radius of earth, it is minus gm by r, right? So this distance, right, irrelevant of any point inside the shell, right, it is equal to, remember we have taken it, guys, this minus gm by r itself. So minus gm by r, right? For any point on inside the spherical shell, the potential is depending only on the radius. Sorry, what did it come here? Right, so you can write it as minus gm by r. Now you add, you will get minus 5 gm by r. That is the potential at the point P. Right, now similarly let us do another question. A satellite is revolving around Earth at a height of 600 km. Find the orbital speed of the satellite and its time period. You are given radius of Earth as 6400 km and mass of Earth is given as 6 into 10 to the power 24 kilogram. Right? So orbital velocity, I hope you remember the expression. It is minus. It is usually, no, why did I write minus? It is gm by r plus h, right? Clear? So r, this is a radius now, so re plus h, if you want you can write it as re plus h, right? So g's value is 6.67 into 10 to the power minus 11. Mass of Earth is given as 6 into 10 to the power 24 divided by Earth's radius has been taken as how much? 6400, and this is 600, right? So 6400 plus 600 becomes what? 7000, right? So I will write it as 7000 kilometers. So it is 7000 into 10 to the power 3, right? So after calculation you will find 7.6 kilometer per second, right? That is the orbital velocity. Now comes the time period section. Right, you can either go by the longer tedious job, or it is very easy by the derivation section. We stopped here. Remember, time is equal to 2 pi r. Here it is 2 pi r plus h divided by the orbital velocity, right? 2 pi and r plus h, you found it as 7000 into 10 to the power 3 divided by What is v? Orbital velocity you have found it as 7.6 kilometer per second, means you will multiply 10 to power 3. So you can cancel 10 to power 3, 10 to power 3. After calculation you will get 5.8 into 10 to power 3 seconds. That is the time period of rotation of this guy. Clear? Very simple problem, right? Later on we'll do good questions.